So we've been looking at normally distributed data and seeing that it's pretty handy to know that our data are normally distributed because we can use things like the 68, 95, 99.7 rule for determining percentile scores for data. Sometimes data looks almost normal, or it might be normal, and we want a quantitative way to tell that. One of these tools is called a normal quantile plot, also sometimes called a QQ plot. Both of those Q's stand for quantile. How can we determine whether data are normal? Well, if data are highly skewed, suppose our data have a long right tail, that's pretty easy to tell that it's not normal. If I have data that has more than one peak, I can tell that that's not normal. Or if it has some outliers, those are all clear signs that the data are not really normally distributed, and we might have different ways of handling them. But what if the data look close to normal? Here's a normal distribution, say, just a sketch, and one with fat tails. So suppose the data in the heart of the distribution here, it looks normal, but then the tails don't die away quickly enough. Or if we had a pointier than normal distribution, suppose I had here's a normal distribution, and everything is looking fine, but then it's a little pointier than I expect. We know the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. If a variable x follows a normal distribution with mean mu and standard deviation sigma, then the standardized variable z, which we obtain by, we've seen, subtracting the mean and dividing by the standard deviation, will follow the standard normal distribution. So x follows any normal distribution with mean mu and standard deviation sigma, and the z-score gives us a way to transform that to a normal distribution with mean 0 and standard deviation 1. How can we use that? Well, I want to generate z-scores for my data and then compare them to z-scores for something that I know is normal. So if my data are normally distributed, a z-value for near the middle here, I expect that to be a value around 0 because I've standardized my data, which means we're seeking a mean of 0. And suppose the distribution I'm looking at is the standard normal distribution. Of course, for both the sample z values and the theoretical z values, I'll get the same values. But what if my data had fat tails? Then I know there's more data out here than I expect. It doesn't die away quickly enough. So what that means, if my z value is 0 here, and I go -1, -2, -3, up here I have +1, +2, +3, we know within 3 standard deviations we're going to have 99.7% of the data. So that'll cover most of our data points. And here what I see is my tails are fat. What that means is that the z values that we compute are going to be more extreme than we expected. And in the middle, they'll be roughly linear, but then when we get up here in the positive values, they'll be more extreme. So this shape is kind of shaped like a backward S diagonal. So we say this is reverse sigmoidal. And whenever you see that, it means that you have fat tails. So can you guess what sigmoidal shapes would mean? If I had thin tails, let's just sketch on the same graph here. If I had thin tails, I'm going to switch to orange. Then I know the data has died down to really low values sooner than I expected. So then we're not going to accumulate very much percentile there. And that's going to give us data that are closer to 0 z-value near the extremes. So this shape, which is sigmoidal, meaning like an S, that means thin tails. But these are both symmetric shapes, reverse sigmoidal and sigmoidal. If my data are skewed, what I'm going to see is compared to the diagonal, I'm just going to have, if I have skew right, that means I have a heavy right tail. So we'll see a distribution of z-scores that stays near the line and then veers up. Typically for skew, you'll see a curvature of this kind. And if it's skewed left, we're going to have veering away from the diagonal line at this end, so this kind of thing. So curvature this way is a skew left, and up here, if we have curvature this way, that's going to be skew right, because it is the right tail, the positive tail, that veers above normality. So let's see how to do this in Google Sheets. My data is in column A. This procedure will always be the same. So in column B here, I want to put my sorted data. Here I'll say sorted X. I love to put labels in so I know what's going on. This is a really nice command, sort. I'll click in column A here. Notice it fills in A:A. That means the whole column. And I didn't have to drag anything, it just sorted all the data. How many data points do I have here? I see that I have 101 data points. And it foolishly considered my X here to be a data point. That's not the case. But it popped it to the end, so it's out of our way at least. The next thing we want to do is have z-scores for these samples. These data are, we can consider them to be samples from some population. So to calculate z-scores, we will take this data point, let's get some parentheses, data point minus the mean of that data point. Command for mean is average. We want the average of the whole column, so we'll do b:b. I got that by clicking in the capital B at the top. And then I'm going to divide by the standard deviation of column B. So that gives me a z-value. It is, not surprisingly, since it's the smallest data point, a negative value, and it is greater than -3. I'd be surprised to get much data more extreme than -3, as we have seen. So here are our z-scores for that data. Now let's remember, the first step I said was to graph the data. If I graph these data, let's take a look. I see just about equal positive and negative data. I don't want a scatter chart though. I want a histogram. There it is. So these data look pretty close to normal to me. I think these are a good candidate for subjecting to this treatment of seeing how they compare to a normal distribution. Let's take a look. There's our histogram. Now the next thing we want to do is generate some equally spaced percentiles. How many data points do I have? I can use a command to determine that without having to count them. I can say equals 1 divided by the number of data points. How many data points are there? I'll use this command, count. My number of data points here in the original data set is 100. So I got 0.01 for that value there. Now I want evenly spaced percentiles, so I'm going to take the value above me and add 1 divided by the number of data points, which we just did. We'll recycle that command. So I'm starting with 100th and adding 100th every time, and this generates evenly spaced data points. Here it would have been pretty easy because it's 100, but we could have any number of data points and this command would work. So my first data point is 1 over the number of data points, and my second is the first value plus 1 over the number of data points. Now I want to calculate the z values that would give me these percentiles. So if I looked up the z's in a z-table, I would get these percentiles. The command to do that, this is to calculate our theoretical z's, is going to be norm inverse, NORMINV. Since we use norm dist to calculate a percentile from a z-score, we use norm inverse to calculate a z-value from a percentile. So we're going to take that value, and then here it's telling me the syntax. Since I've already standardized my data, I'm going to compare to the standard normal distribution, which is the one that has a mean of what? Of 0, and a standard deviation of 1. So there is my z-score for the first percentile. When I get up to 50th percentile, my z-score should be 0. Now that's working. So we want to get a z-score of 0 when we get to 50%, since that is our mean. These were all negative scores. Now we're going to go to the positive half of the z table, right side of the distribution. And everything is worked out here because I got to 1. And I can't compute a z-value for the 100th percentile. Remember, you can't be in the 100th percentile on the SAT or ACT because the percentile is the percentage of the population that's less than the value that we're considering. Now let's plot our sample z versus theoretical z. We want the scatter chart. It has not added an x-axis for us here, so let's make sure we have an x-axis. I want the x-axis to be not the sample z, but the theoretical z. Select a data range. Our theoretical z is in column F. So I'm typing F:(F) there. And I want my series to be sample z, which it is. So here we have x-axis, theoretical z, and y-axis, sample z. So we can see that these data look pretty linear. If anything, I'd say there's a little bit of, that's sigmoidal shape. It's like a long stretched out S. So we remember that means that the tails are a little bit thin here. But this data looks over a wide range to be normally distributed to my eye. So that is the procedure for making a normal quantile plot. Remember, we took the data and sorted it. We calculated z values by subtracting the mean and dividing by the standard deviation. Next, we generated evenly spaced percentiles and computed theoretical z's for those values using the command norm inverse, which takes a percentile and converts it into a z value.